So, let me revisit bounded variable linear programming problems. I will continue with the example that I did last time, because I have a feeling that I did not sort of show you all the possible pivot steps. So, I thought I will complete the example, and so this was the last table I gave you, and remember we had to do phase 1, phase 2. So, this refers to phase 1 objective function and this refers to phase 2 objective function. So, we have two artificial variables, right. So, as we continue, see here, this is the first negative, in fact this is the only negative entry in the top row. So, x7 is a candidate for entering the basis or becoming a basic variable. So, then we take the ratios. So, here the ratio would be 3/2, here the ratio would be 3/5, and for a negative entry, remember, since the upper bound constraint on each variable is 5. So, I will do it as 5 minus 5/2 divided by 1/2, and this comes out to be 5/2 into 2, which is 5. So, therefore, I choose the minimum. That means, my theta 1 is 3/5, theta 2 is 5, and theta 3 is also 5, right. Theta 1 is 3/5 because of the positive entries, the ratio, this is the minimum ratio. Then your theta 2 corresponds to the negative entry, which is 5 here, and theta 3 is the upper bound, which is 5. So, theta 1 is the minimum, therefore, I will pivot on this one. So, x7 now becomes a basic variable, and in its place xa2 goes out of the basis. So, first artificial variable goes out of the basis. I need not make this computation, because remember, if an artificial variable leaves the basis at any time, then it will not re-enter the basis. You try to figure it out also. Why? Because, so in any case, I did the computations here for this artificial variable, artificial column also. It was no need to do it. Fine. So, now you will see that the new zj minus cj, because we will be making zeros here, both the places, and please check the computations. I will not be very sure, but anyway, just make sure that the computations are okay. You know the steps. So, you have to make 1 here and zeros elsewhere. So, this is how I do the pivoting, and these are my new right hand side objective function value. This you can also check. Maybe we can make a quick check here. See here, this is 3/5, and to make it 0 here, I have to multiply this by 4 and subtract. So, that means it should be minus 47 minus 4 times you have to subtract. So, which means 6. Oh, okay. Sorry, 3/5. This becomes 3/5. So, 3/5 into 4. So, that is 12/5. Right. So, you have to multiply this by 4 and subtract from here. So, that is 12/5 subtracted. So, actually this should be, sorry, minus 12/5. Okay, this is the new value of the objective function, and also make sure that these computations are okay. Fine. So, this is your next tableau here, and if we look again at the top row, look at the most if the first negative entry in the top row. So, this is minus 4/5. So, this will be a candidate for entering the basis, right, and here you have one positive entry. So, this would be 9/4, the corresponding ratio is 9/4. In this case, it will have to be 5 minus 3/5 divided by 2/5, which you can see is large. 25 minus 3 is 22, 22/11. So, this is 11. Then 14/5. So, here the corresponding computation will be 5 minus 14/5 divided by 1/5. So, this will turn out to be 25 minus 14, that is 11, that is also 11, right. So, therefore, your theta 2 is 11, theta 1 is 9/4, and theta 3 is 5. So, here again you will be pivoting on this one, right. So, here again this is 4/5. So, let me make this as 1 and 0 zeros elsewhere. So, we do the pivoting, and this is the last column. So, make sure that this computation also should be all right. So, you can verify for yourself, you know the steps here. So, anyway, this will be your next table, and you see that now this is the end of phase 1, because this value is 0. both the artificial variables. So, I did not make the computation for this artificial column. You are, when this one is entering the basis, is becoming a basic variable, this one is becoming non-basic. So, then my the use of artificial variables is over, and I can now start with phase 2, and you see the top row for phase 2 is already there. So, I can start from here, right. Now, just want to make one observation here. You see this can enter the basis now, but you see this is negative, but the corresponding column here is also has all negative entries. So, in a regular simplex algorithm, you would have concluded that the problem is unbounded, but here of course, there is no question of the problem being unbounded, because all your variables are less than or equal to 5. So, the variables cannot take very large values here, and in any case remember this is x 1 prime. So, you have this relationship that x 1 prime is 5 minus x 1. Okay. So, therefore, because we are making this transformation in the table whenever a variable reaches its upper bound. So, therefore, this is showing like this. In any case, the bounded variable linear programming algorithm allows us to continue with the pivoting even when the entries in the corresponding pivoting column are all negative. So, you know that. So, we will do it here. This would be the corresponding ratio will be 5 minus 9 by 4 divided by 5 by 4. So, this gives you what 20 11 by 5, right. Then this would be 5 minus 3 by 2 divided by half. So, which is 10 minus 3 7 7 this is 7. Okay. 10 minus 3 7 7 by 2 into 1 by 2. So, that becomes 7, and then 5 minus 13 by 4 divided by 1 by 4, this is 20 minus 13, that is also 7. Okay. So, this is the minimum ratio. Therefore, we will pivot on this one, and now you can continue with the simplex algorithm. So, that means this variable, when this variable becomes basic, right, x 1 prime is now a candidate for becoming a basic variable, which means that x 1 becomes 0. See, so far x 1 prime was non-basic. So, that meant that your x 1 was at level 5. Once x 1 prime becomes basic, so it is not that x 1 will become 0, because just see the level at which x 1 prime will come into the basis is 11 by 5. So, that means the corresponding value of x 1 is what? If x 1 prime is 11 by 5, this is 5 minus x 1. So, therefore, x 1 is 5 minus 11 by 5, which is 25 minus 11, which is 14 by 5. So, this is the current value of x 1. So, remember, when you at the end of the algorithm, when you have optimality with respect to this objective function also, you will see all the variables which are at prime level, and correspondingly use the transformation to get the right value of the variable. So, this way you can continue with the bounded variable linear programming algorithm. Okay. So, I thought that at least this will give you a this, and sit down when you look at this algorithm, please sit down and check that the entries are all correct or not. Okay. Now, I want to talk about another aspect of the simplex algorithm, where actually you can, because you see when the problems are small, I can carry the whole tableau along with me, make all the computations, and so it does not take much time. But in case you have a problem, and which is normally the case, like let us say I have 1000 variables, and let us say 1500 constraints. Even in a computer, 1000 variables, okay, and 1500 constraints, you do not expect any computer output to have to carry 1500 no, I should, the other way, sorry, we should have said that 1500 1500 let us say variables, yeah, okay, sorry, the number of variables is always more than the number of constraints, and you have 1000 variables, 1000 constraints. Okay. So then that means you have 1500 columns, and if you end up adding artificial variables also, then you see the number of variables will be very large. So your tableau size would be very big, and you cannot glance at it, you cannot look at the whole thing, and there is no point, because you see the computations do not require you to actually. So let us revisit the simplex algorithm. Okay. What we are trying to say is that you need the quantities we need are basically, I need B inverse at each iteration, right. Okay. Once you have B inverse, then I can immediately compute my Cj minus Zj, which is equal to Cj minus Cb B inverse Aj. So if I have my original tableau, I have the Cj's and Aj's, so I can compute this for all j. Okay. And I need the right hand side. So right hand side, your the value of the objective function is Cb B inverse B, and your feasible solution, basic feasible solution, is given by B inverse B. So these are so all this is computable, provided I have my current B inverse. That means I need to update my B inverse at each iteration, and I showed you that if you carry this, then this becomes, see, remember this was the extended basis size m plus 1 by m plus 1 that I am carrying at each iteration, and I update it. And how do I update it? The idea behind it is that, and so if I have this and I have my tableau, so that means if you have your C entered somewhere, you have your A and you have your B. So if I have this stored somewhere in my computer, the starting value you can say 0. If I have this stored somewhere in my computer, then what I can do is I can recall a column from here, a non basic column, right, and if I multiply this by Cj Aj, just the top row. So if I keep this extended basis inverse somewhere, in fact I do not even have to store this, right. So I just keep this extended this somewhere, and I have my original problem stored in the computer. I will recall, I start recalling the first non basic variable, second, and so on. So I multiply the top row with this, and that gives me Cj minus Zj. So I will keep multiplying the top row with my non basic columns, and the moment I hit a j for which this is less than 0, I know that this is my pivot. By the Bland's rule, I know that this is my entering column, this has to become a basic column, and then I will do this computation. So I will then compute the Yj. So only for the column which has to enter, which has to become basic, I do this computation. I do not have to do it for all others, right. And then I do this, and from here I also have, see, I can multiply B inverse with B. So I will have the right hand side vector here, B inverse B. So suppose you have this, and of course your objective function value here, objective function. So sorry, you have this B inverse B. So then I will have this column. So I decide the pivoting element. So I will start taking the ratios, and the moment I get the corresponding, so that means for all positive entries here, I will take the corresponding ratios, and I get the element YRS. Oh, okay, this is YRJ, right. So this will be my pivot element. Once this is my pivot element, I can just pivot on this column. So that means I keep this aside. I now pivot on the YRJ and make a 1 there, 0 elsewhere, and similarly, remember, I do the same thing with this. The row operations I do with this, and I do the row operations with this right hand side column. Once I do that, then I get my new basis inverse, and I can. So you see what is saving. So this is what I am describing to you, is the revised simplex algorithm. So the revised simplex algorithm, the idea is, and this is how a computer handles this. So we can store the original problem, we can keep updating our basis inverse at each iteration, and that we know how we do it. We do it by selecting the column which has to become non-basic, which has to become basic. Then by taking the ratios, I can find out the pivoting element. Once I know the pivoting element, then I can pivot here. I do the same computations here, and I get my new basis inverse, new right hand side feasible solution, and the objective function value, right. And then I can continue again, just take the top row of the new revised or the new basis, extended basis inverse, and then I multiply it by each non-basic column, and the moment I hit a negative Cj minus Zj, I select it for pivoting, right. Okay, so you can see that the amount of saving in space computations is tremendous, and that is why one can handle large size linear programming problems. But even this kind of computations became too, when this transatlantic problem had to be solved, the communication problem had to be solved, the size became even beyond the best computers available at that time. So we will come to that at the end of the course, when I can spend some time on the alternatives to solving linear programming, alternatives to the simplex algorithm. We will talk about it. But currently, certainly the programs that are now written for the simplex algorithm only use the revised simplex algorithm, because we do not need to convert the whole tableau at each iteration. I do not need that information, right. I just need to know which is the column which has to enter the basis, and then I just pivot on that column, and I need to update my basis inverse, that is all, right. Once I have the new basis inverse, then I can compute all the required quantities to continue with the simplex algorithm. Okay. And yeah, now another thing is that even this becomes too big to store every time. So what they do is they use the, let me explain, and I will try to be slow, product form of the inverse. Yes. Now here again, this is the same idea that I had introduced in the beginning, when I told you that when you do any row operations on a matrix, for example, if you take a matrix A, I want to multiply rth row by a constant C, for example. So I just want to multiply the rth row of this matrix by a constant C. What does it mean? I can also multiply the corresponding C, that means take the elementary matrix 1 0 0 0 1 0, and then the rth row you will have a C here 0 0 0 1. So this is my elementary matrix, which I obtain from the unit matrix by multiplying the rth row by C. So then this will be my elementary matrix, and this, when I pre-multiply the matrix A by this matrix, I get the corresponding result, right. So this we used earlier also, and the same idea I am going to continue with here. Okay. So when you are pivoting on on the column yj, for example, what do? I have, see, the entries are y1j, y2j, yrj, and ymj. This is my yj column, right, and this is my pivot entry. So what will I do? I divide by yrj, right. So if I write down, see, that means consider the unit matrix, unit m by m matrix, in which the jth column is, now what is the jth column? The jth column will be, it will be 1 by yrj. So I am just writing the jth column, right. In the unit matrix, I just replace the jth column by hold on, in which the rth column, in which the rth column is, so this is the rth column, well, because rth column will have a 1 here. So, this is rth column, okay, 1 1 or rj. Then for example, I want to make a 0 here. So, what do? I multiply the rth row by y1j and subtract. So, this will be minus y1j upon yrj. Next entry will be y2j upon yrj, and so on. And the last entry here would be minus ymj upon yrj. So, the unit matrix in which the rth column has been replaced by this. Now, if I pre-multiply, so that means I pre-multiply the current basis inverse by that matrix in which the rth column of the unit matrix has been replaced by this, because this is all the pivoting that you do, right. You multiply the first row by y1j and subtract. So, the first, that means you multiply this row by y1j and subtract when you where you have divided this entry by yrj, right. So, y1j and you subtract it. So, these are all the pivoting elements, pivoting operations that you do, right. So, I replace the rth column of the unit matrix by this, and then if I pre-multiply the current basis inverse by that matrix, I will get the new basis inverse. And of course, I have not done the calculations for this also, but the same thing will apply. So, that means you can, instead of keeping the whole thing like this, the B inverse, essentially I am just concentrating on B inverse. If instead of keeping this as this, we can keep it as a product of. So, every time at each iteration you have this column, and you know that this is the rth column of the unit matrix. So, then I can immediately write down my corresponding matrix that I need to pre-multiply with, right. So, in which the rth column is this. So, you can store the basis inverse as a product of I should maybe I will just coin a new word here, inverse as a product of iteration matrices, something like or pivot matrices, pivot matrices as a product of pivot columns. So, this is my own term, maybe let us say, but you understand that I can just store the inverse as a product of these, and so when I need it, I can simply multiply them all and then get my B inverse, then get all my other quantities and continue with the algorithm, right. So, that means now you know when you get an output from a given any simplex algorithm, you will understand that it will give you the basis inverse. It may give you in this form, maybe it may m plus 1 by m plus 1, then it will give you the right hand side with, so you can read the basic feasible solution, and that is it. Okay. So, you can continue with, so this is a definite saving. It makes it quicker because you are not computing, your number of computations has gone down drastically, and you require less space also. So, it allows you to solve real large problems by the simplex algorithm. So, this is where we end with the revised simplex algorithm. So, we will continue revisiting, and of course, you can modify this when you are applying this to the bounded variable problem, right. You or if you have phase 1, phase 2, then also you will be having two objective function, two such rows here, and you can do the same thing. You can simply modify once you know what is where and why. So, once you understand that, then you can modify the whole thing, right. Okay. Papadumitro in his book says that linear programming theory is very interesting by itself, and you have seen how versatile. In fact, I have not shown you so many other aspects which we will see now of the simplex algorithm, but and so that would have been enough. The linear programming theory by itself would have been enough, but now I show you another interesting aspect of linear programming theory, and that is duality. So, let us just first start with consider a general form of the LPP. Of a linear programming problem, right? And the general form would be where I say that this is minimize z equal to C transpose x subject to AIX greater than or equal to BI. I'll explain in a minute, where I belongs to M. So, inequality constraints of the greater kind, and here see the notation is I have been using AJ for a column of A, and when I do this, this is the ith row for jth column here. This is for jth column of A, and AI is the ith row of A. So, I suppose should not be confusing. So, small a refers to the row. So, therefore, it is a row form. Therefore, I am writing this as AIX greater than or equal to BI and AIX equal to BI for I belonging to M bar, right. And we say that xj is greater than or equal to 0 for j belonging to n, and xj 0 for j belonging to n bar. That means some variables are restricted to be non-negative, some variables are unrestricted, some constraints are inequality constraints, and some constraints are equality constraints. So, this will be a general form of a linear programming problem. I had earlier shown you that we can convert all linear programming problems to the standard form by either adding slack variables or surplus variables. So, let us do that. So, when I write the standard form, okay, this is now the standard form would be minimize, yeah, okay, to the standard form. What do I need to do? Because in the standard form all variables are non-negative. So, here we can write for j belonging to n bar, let for j belonging to n bar, let xj be written as xj plus minus xj minus, where xj plus and xj minus are greater than or equal to 0. So, this is always possible. Any number can be written as a difference of two non-negative numbers, right. So, we will replace all xj's which are unrestricted in their sign by this expression xj plus minus xj minus, and where xj plus and xj minus are all non-negative. So, what will happen, say for example, for the coefficient here for xj plus will be plus cj, for xj minus will be minus cj, right. And similarly, here the column corresponding to xj, the column aj, now you will have a column aj appearing here and a minus aj also appearing in the constraints, right. So, standard form therefore would be minimize, maybe you can say this is z bar, which is c bar transpose x, because now your c bar has changed, and maybe you can say that this is x hat, right, subject to ai, okay, or maybe in this case I will not use the same this thing. What we can say is we will simply say that a hat x hat is equal to, your b will not change, right. The right hand side does not change, because here I would have added surplus variables minus xsj, and you will have this thing. So, the right hand side remains the same, and now you have this thing that x hat is greater than or equal to 0, right, where x hat contains surplus variables surplus variables as well as variables of the type variables of the type xj plus and xj minus for j belonging to n bar. Okay. So, the x hat is your new set of variables, and this will be your standard form of the linear programming problem. Now, let us look at the optimality conditions for the new formulation, right. So, here for example, what would be the condition? Now, you can consider first a variable where j belongs to n. So, for these variables, for j belonging to n, optimality criteria for xj is Cj minus Zj greater than or equal to 0, right. That is Cj minus Cb B inverse Aj is greater than or equal to 0. Yes, for j belonging to n, this is my optimality criteria. So, I will just write them down and let us look at this. Now, for j belonging to n bar, remember for j belonging to n bar, you are going to have two columns Aj and minus Aj, right. And so, for j belonging to n bar, my two conditions would be I will have Cj minus Zj greater than or equal to 0 and minus Cj, remember minus Cj and the Zj, because Zj is Cb B inverse Aj, right. Zj is Cb B inverse Aj. So, now for xj plus, it is going to be Cj minus Zj. For xj minus, it will be minus Aj. So, that becomes, and this will be minus Cj. This is plus Zj, same quantity, because the column is the same, it is the sign which is greater than or equal to 0. So, what does this imply? These two together imply that Cj minus Zj is 0. So, for all j belonging to n bar, my optimality condition is that Cj minus Zj is 0. That is Cj minus Cb B inverse Aj is 0. Okay. Now, consider for surplus variable xsi, what is the corresponding column? Your asi is nothing but ei, because you have added it to the ith constraint here. So, for I in m, you added a surplus variable here. So, the corresponding column is minus ei, minus ei, sorry, right. Therefore, and your csi is 0, right, because it is a surplus variable. So, therefore, Cj minus Zj is equal to 0 minus Zj would be what? Cb B inverse ei and plus. So, this should be greater than or equal to 0. Is it okay? For surplus variables, have I done it rightly? Because we are writing greater than kind, so it will be minus ei. That is right. It has to be minus ei. We add a surplus variable, so this becomes Cb B inverse ei, which means that the vector Cb B inverse I is greater than or equal to 0, I belonging to m. So, the components here, that means suppose I for all I in m, I have added a surplus variable here. So, therefore, the corresponding components of Cb B inverse I are greater than or equal to 0 when I belongs to m, and I cannot say anything for I in m bar for the sign of Cb B inverse, right. I cannot say anything. The signs of the components of Cb B inverse. See, remember, this is an m dimensional vector, and of course, yes, I should have said here that m union m bar, we want to call the cardinality is m. That of course assumption is there. So my total number of variables was n here. That means n union n bar, cardinality of n plus cardinality of n bar is n, cardinality of m plus cardinality of m bar is small m. So those dimensions are still there, and so I mean I'm assuming that, and so here for all I in m, the corresponding component CBB inverse must be non-negative, right. So once you have this, and you see that this is what they satisfy for j in n, and for j in n bar the condition is that it must be 0, right, this must be 0. So now let me define the dual problem, or what would be best is that I write it here. Okay, yeah, I think that will be best. So let me now write the dual problem here, okay, so that you can then match the things. So what I will do is I will write my dual variable y, the column as B inverse. Now if you are, see, this is the convention here, I am doing it, this is a row vector. So if you will have to write this and this, so that it becomes, so that y or okay, to keep it safer, simpler, y is a column. So therefore this is CV B inverse transpose, because this is a row, I am writing this as a row vector. So when you take the transpose, it becomes a column vector, right. So y is CV B inverse transpose. If I do this, I define the dual. So define the dual problem See, remember in the primal problem we try to find a basis B which will give me an optimal solution. That means for which the optimality conditions will be satisfied. And now I write the other side of the problem, that is, now I am saying define the dual problem such that you are maximizing what is the this thing, we can write this as psi equal to, yes, B transpose y, okay, subject to, let me write it down. And so here this was for I belonging to M, remember. So now I will try to define the dual problem keeping these optimality conditions in mind, and that is how we will define the dual. That means, so you can see that if primal problem is concerned with feasibility, maintaining feasibility and improving the objective function value, here the primary concern of the dual problem will be to satisfy the optimality condition. This is the idea. So maximize this subject to, so remember here this is subject to, we will say that for I subject to yi greater than or equal to 0, I belonging to M, okay, corresponding to this, and corresponding to this yi for I belonging to M bar, because we are not able to say anything about the sign of the corresponding dual variable when I is in M bar. And then for xj non-negative, what do I have here? J belonging to N, the condition is that, so here this will be, you can write this as, see, this is CBB inverse AJ, it is a single number, so I can write it at its transpose, right. So that will become AJ transpose Y, this would be less than or equal to CJ, right. See here, if you write this, this quantity is less than or equal to Cj, that is your constraint, right, for j belonging to n. So that corresponds to this, right. And for when this is unrestricted, when your j is unrestricted, then we got this condition, that is AJ transpose y is equal to Cj for j belonging to n. So this is your dual problem. Okay. Now of course we can also do, so now you, I mean you can, and let us see, you can immediately write down. So once I have this dual problem, let us see what kind of information we can extract from it, And what does it, how can we use it? See here, if you look at this and I multiply, because my for j in n, xj is non-negative. So, if I multiply this constraint by xj and add for all j belonging to n, the inequality does not change, right. And then here, because this is equality and the sign of xj is immaterial, this is unrestricted. So, the inequality will not change. So, let me multiply this by xj and also this by xj and add. What do I get? So, this will give me xj aj transpose a, sorry, y, right, summation j belonging to n plus summation xj aj transpose y, j belonging to n bar, right. This will give me summation, this will give me less than or equal to, right, because this contributes to less than or equal to sign, less than or equal to cj xj. So, that means now I will add for any x feasible for p. Let me write this problem as my primal problem p, right, and this as my dual problem d. So, we will always refer to PD as the pair, primal dual pair, right. So, is feasible for p and y is feasible for d. Okay. So, for d, right. So, I am assuming that I have a y satisfying this set of constraints, I have an x satisfying this set of constraints, then you have cj xj, right. And here now you can rewrite this as, again, see, this is a single, this will be, see, how will you read this when you sum up as xj aj transpose y. So, this is actually summation xj aj transpose y, j belonging to your n union n bar. Okay. So, this I can rewrite as, take the whole this thing, this will be y transpose, see, this is a single number. So, I can take a transpose and it will not change. So, y transpose aj xj, right, I am taking the transpose of this whole thing, right. So, this will, and this, remember, aj xj is greater than or equal to, see, these constraints you can also write as ax greater than or equal to b, right, equal and b, right. So, this whole thing becomes ax, you are summing over j, because y transpose I can take outside, remember here y I can take outside, then I am summing over this, which is the same thing as summing aj xj, so which is greater than or equal to b, right. So, this whole thing is greater than or equal to y transpose b, and then this is less than or equal to c transpose x. Remember, this is over j. So, this is your c transpose x, this whole quantity, because you have equality constraints and greater than kind constraints. So, this whole thing is greater than or equal to y, b, and so this becomes y transpose b is less than or equal to c transpose x. So, this is the first lemma of the duality theory, which says that if you have a feasible solution for the primal and you have a feasible solution for the dual, then the objective function value for the dual will always be less than or equal to the corresponding objective function value for the primal. So, take any primal dual feasible pair, you will have this inequality. So, in other words, what we are showing is that this is a maximization problem, this is a minimization problem. So, the max objective function value will always be less than or equal to the min objective function value, okay, for the primal. And now, I will, as an exercise, ask you to write the dual problem. So, write the dual problem, this is a simple exercise, write the dual for the standard form of, LPP, which is minimize z equal to c transpose x subject to ax equal to b, x greater than or equal to 0. So, please do it and we can check it next in the next lecture. I can give you these, and because most of the time I'll be I just took the general form to demonstrate to you how the dual problem can be formulated in the most general case, right. Now let us just take up an example here. We'll just demonstrate to, so consider this problem. Consider the LPP minimize z equal to x1 plus x3 subject to x1 plus 2x2 less than or equal to 5, then x2 plus x3 or 2x3, sorry, 2x3 is equal to 6, x1, x2 greater than or equal to 0, x3 unrestricted. Suppose you have a linear programming problem in this form. So, I have deliberately chosen it a little different from the form I stated, but see, it does not matter. No? If you have a greater kind inequality, if you have a less kind, then you can multiply the whole thing by minus sign and you can get it of the greater kind. So, all these things are easily manipulated, no problem. So, anyway, the best thing would be, see, we can do it two ways. Okay. So, as I told you, we convert the problem to the standard form. Right, which would mean that for x3 I will have x3 plus and x3 minus. So, this will become minimize z hat equal to x1 plus x3 plus minus x3 minus, right. For x3 it is unrestricted. So, I will substitute substituted by this expression. Then here we will have to add a slack variable. So, this will be subject to x1 plus 2x2 plus x s1 equal to 5, right. And then you will have x2 plus twice x3 plus minus twice x3 minus equal to 6, and now all the variables are non-negative, x1, x2, x3 plus, x3 minus, xs1, all the variables are non-negative, right. Fine, but you want to follow the rule here and then write the dual. Let us do that simply, yeah. Or if you want, I can derive it from, see, the only thing is that here, remember, this constraint is less kind. I gave you the rule for writing the dual problem, and your constraints are either greater or less. So, what would you want to do? See, if I can convert this to minus type also, minus aix less than or equal to minus bi, but how will that change? You can guess and say that the corresponding variable yi will be less than or equal to 0. Why? Because remember, see, it was simple. How did I derive this condition, yi greater than or equal to 0? The condition I derived was from, because for the surplus variable the corresponding coefficient in the objective function was 0 and the column was minus ei. Now, when I add a slack variable, the column is plus ei. So, and the coefficient is 0. So, you have minus cb b inverse aj less than or equal, greater than or equal to 0, right, and aj is your, so minus cb b inverse and aj is your ei. So, this is greater than or equal to 0, which means that the corresponding component, ith component, is less than or equal to 0. So, when you have for a minimization problem, if you have less than or equal to constraint, the corresponding dual variable will have a negative sign, less than or equal to 0, right. So, that is it. So, that is all you have to remember. So, in that case, now you can write the dual quickly. So, this will be maximize psi equal to, and so okay, I'll write it and then I want you to sit down and, so this will be 5, the right hand side becomes 5 y1 plus 6 y2, right, subject to, remember the columns become the rows transpose. So, a particular column here, this will become, so this will be y1, this only entry here, and y1 would be, see, this is less than or equal to 1. Then the second column 2y1 plus y 2, right, this will be less than or equal to, less than or equal to the corresponding coefficient 0 here, y2 is not appearing here, right. And then for the equality, for the unrestricted thing, I had equality constraint. So, the corresponding column for this thing for x3, the corresponding column for x3 is simply 0 2, right. So, 0 2, so that means y2 is equal to, in this case it will be 1, right, and y1 less than or equal to 0, y2 unrestricted. For equality constraint, your corresponding variable is unrestricted, which you have. So, the second constraint is unrestricted. So, actually now you see that the correspondence is the dual variable corresponds to a primal constraint. Okay. So, y2 corresponds to this constraint, y1 corresponds to this constraint. Since this is of the wrong kind, we so the wrong kind in the sense that I formulated it for greater. So, there the y corresponding variable was non-negative, here it is less. So, the corresponding variable is less than or equal to 0. So, this is your dual problem. Okay. So, in the exercise, in the assignment sheet, and also while you are going through this material, you should sit down and write down the dual, learn to be very familiar how you write down the dual problem corresponding to any form of the LPP. You can either convert it to the standard form, and then, as I told you, do it as an exercise, write the dual for the standard problem. I'll revisit it in the next lecture and try to show you how in the standard form also you can immediately write the dual. So, once you have this, now we will have very interesting interpretations for the dual problem, for the dual variables, and especially there are a lot of economic interpretations of the dual variables also. So, this adds the richness of the linear programming theory. So, I will continue with this in the next few lectures.